Alarms are blaring. The stick shaker rattles violently against your hands. You're pulling back on the yoke with everything you have, desperately trying to get the nose up. But no matter how hard you pull, an invisible force inside the flight computer is fighting against you, actively spinning the trim wheel forward and forcing the plane down into a dive. In modern commercial aviation, safety relies on a strict engineering rule: redundancy. Every critical system has a backup. If one sensor fails, a second, independent sensor checks the data, preventing a single hardware glitch from causing a disaster. The Boeing 737 MAX bypassed this rule. Hidden deep within its flight control computers was a software system capable of commanding the aircraft into a nosedive, and it took its orders from a single, fragile external sensor. By removing the safety net of dual inputs, a world-class airliner was engineered into a fatal trap. To keep pace with their competitors, Boeing needed to fit new, highly fuel-efficient engines onto the existing 737 airframe. These larger engines couldn't simply slide under the old wings. To maintain ground clearance, engineers had to mount them further forward and higher up on the aircraft. This physical change altered the plane's aerodynamics. During maneuvers requiring high engine thrust, the aircraft's nose would naturally pitch up higher than intended, creating a severe risk of an aerodynamic stall. Instead of redesigning the physical airframe, Boeing patched the hardware problem with software. They created the Maneuvering Characteristics Augmentation System, or MCAS. This diagram outlines MCAS. Step 3 shows if the system detects the nose pitching dangerously high, it automatically swivels the horizontal tail to force the nose down. Without any input from the crew, MCAS could take control and push the aircraft toward the ground. A physical instability in the airframe was covered up by an automated loop, granting the computer the authority to override the human beings in the cockpit. The trigger for this automated sequence sits on the outside of the fuselage. It's a small, blade-like instrument called an angle of attack sensor. Looking at this technical drawing, the angle of attack is the specific angle measured right here, between the airplane's reference line and the oncoming airflow. The 737 MAX has 2 sensors, but MCAS draws data from only one. If that single sensor malfunctions, it sends falsely high readings. MCAS trusts that broken signal and repeatedly pitches the plane down to correct a stall that isn't happening. There was a built-in safety feature, an AOA disagree alert, meant to warn pilots if the 2 sensors provided conflicting data. But on more than 80% of the MAX fleet, a software error rendered this alert completely non-functional. By relying entirely on one unverified data stream, the system's architecture created a literal single point of failure. One snapped vane could doom the aircraft. If an automated system was seizing control, a logical question remains: why didn't the highly trained flight crews simply identify it and turn it off? Boeing's primary sales pitch for the MAX was cost efficiency. They promised airlines that pilots already certified on older 737s wouldn't need expensive new simulator training to fly the new model. To keep that promise and avoid mandatory retraining, Boeing aggressively minimized the scope of MCAS in briefings to the Federal Aviation Administration. They framed it as a minor, background extension of existing speed trim systems. Boeing requested permission to remove all references to MCAS from the pilot's flight crew operations manuals. The FAA approved the request. Flight crews were intentionally blinded to the existence of a system with the power to push their aircraft into a dive. The final layer of redundancy, human intervention, was bypassed entirely. On Lion Air Flight 610 and Ethiopian Airlines Flight 302, the architectural flaws materialized. In both flights, the single active sensor failed and fed erroneous data to the computer. The sensor failure triggered a chaotic cascade of contradictory warnings. Stick shakers rattled, dials disagreed, and multiple warning lights flashed, overwhelming the pilots with confusion. Fighting through the cacophony, the crews struggled against a system they didn't know existed. MCAS activated repeatedly, ultimately forcing both planes into unrecoverable dives. Years earlier, during a simulator test, a Boeing test pilot experienced an uncommanded MCAS activation. He noted it took more than 10 seconds to react, describing the resulting condition as catastrophic. Despite this internal simulator data and the fragile single-sensor architecture, the aircraft was certified as safe and delivered to airlines around the world. The tragedy was hard-coded into the flight computer long before the planes ever took off. Redundancy was discarded to keep development and training costs low. These crashes were the mathematical result of abandoning aviation's most rigid safety standard. A single point of failure was built into the system, and it performed exactly as engineered.